Hi friends, welcome back to our YouTube channel. Today we have to discuss about General Register Organization in Computer Organization and Architecture course. A part of the computer system performs a bulk of data processing operations is called as Central Processing Unit, that can be simply called as CPU. That means CPU is mainly used for performing a large number of data processing operations. CPU is made up of mainly three components. The first component can be called as a register set. The second component can be called as ALU. The third component can be called as control unit. These are the three major components of the CPU. First one is a register set. A register set is nothing but a set of registers that are used for storing the operands and also for storing the intermediate resultant values during the execution of instructions. While performing a particular operation, we require some operands. That operands are stored in the registers. After performing the operation, whatever the result we are getting, that result is also stored in the registers. Next one is ALU. ALU is mainly used for performing arithmetic and logic operations. Arithmetic operations such as addition, subtraction, multiplication, division, increment, complement, etc. Logical operations are nothing but logical and, logical or, and not operation. These operations can be performed by the arithmetic and logic unit. Next one, control unit. Control unit supervises the transfer of information between the two registers and also instruct the ALU to perform a particular operation. So, control unit can supervises both register set and also ALU. Whenever we are transferring the information from one register to another register, that can be supervised by the control unit. Suppose we want to perform a particular operation, that operation can be performed by the ALU, that can be instructed by the control unit. Next one is, we already know that two types of accessing. First one is memory accessing, second one is register accessing. Memory accessing is nothing but the time taken to access a particular data from the memory. It is a very time consuming operation. Whereas register accessing is nothing but we have to access the data that is stored in the registers. So register accessing is more convenient and most efficient to transfer the data. So there are several number of registers, processor registers in the CPU. These registers are communicated with each other by using a common bus system. That means CPU contains a large number of processor registers. These registers are connected together by using a common bus system. By using that common bus system, we are transferring the data between the registers can be done. So that register accessing is a faster accessing operation when compared to the memory accessing operation. So register accessing can be done very fastly when compared to the memory accessing. Next one. This diagram shows the organization of 7 CPU registers within the CPU. So these are the 7 processor registers: R1, R2, R3, R4, R5, R6, R7. These 7 registers can be called as processor registers. How they can be organized, that can be explained with this block diagram. The output of each register is connected to 2 multiplexers to form the 2 buses, bus A and bus B. Here, multiplexer A contains 8 inputs. Among that 8 inputs, we have to select only one input. That input can be passed to the arithmetic and logic unit. Here, cell A is nothing but selection inputs of multiplexer A. By using that 3 selection inputs, we are selecting only one processor register. Whatever the processor register that is selected, the content of that processor register can be sent it to the arithmetic logic unit. Next one, these are the selection input lines for multiplexer B. These selection inputs are used for selecting only one register among the 8 processor register. Whatever the register that is selected, that can be passed to the arithmetic and logic unit through the bus B. Okay, suppose 0, 0, 0. Then we have to select the we do not select any register, only the input is selected. That input can be passed to the arithmetic and logic unit. Whenever selection inputs of multiplexer A value is 0, 0, 0 and selection inputs of multiplexer B values are 0, 0, 0, there is no processor register is selected. At that time, only input is selected. Whatever the content is there in that input, that can be transferred to the arithmetic and logic unit. After that, it can be connected to the output of the bus system. Whenever selection inputs of multiplexer A values are 0, 0, 1 and also selection inputs of multiplexer B values are 0, 0, 1. So R1 register is selected. Also here R1 register is selected. In the same way, 0, 1, 0, 0, 1, 0, R2 register is selected here. Here also R2 register is selected. That can be passed to the arithmetic and logic unit. In the same way, selection inputs of multiplexer A contains 1, 1, 1. Selection inputs of multiplexer B contains 1, 1, 1. Here R7 register is selected. Here R7 register is selected. Whatever the content is there in the R7 register, that can be passed to arithmetic and logic unit. Here also the content of R7 register is transferred to arithmetic and logic unit through bus A and bus B. Next one, uh, these bus inputs can be formed as input for the arithmetic and logic unit. Whatever the source register that is selected, the content of the source register is transferred to the bus A. The content of bus A can be formed as input for the arithmetic and logic unit. In the same way for multiplexer B, after performing the operation within the ALU, whatever the result we are getting, that result can be passed to the output value and also can be formed as input for the 7 processor registers. So the result of the arithmetic logic unit after performing the operation, that result is loaded into the one of the 7 processor registers that is selected by using 3/8 decoder. Whatever the register that is selected by using 3/8 decoder, into that register the content of the result of the operation through the arithmetic logic unit is loaded into a register that is selected by the 3/8 decoder. Suppose here cell D is nothing but selection inputs of the decoder. Okay, suppose this values is 001. Then R1 register is selected. Then R1 register is ready for receiving the result of the ALU operation by applying the clock pulse and enabling the load input. Suppose this value is 101. That is R5 register is selected. The result of the ALU operation is loaded into the R5 register by enabling the load input of the R5 register after applying the clock pulse. Suppose selection inputs of D values are 111, then R7 register is selected. The result of the operation is loaded into the R7 register by enabling the load input of R7 register by applying the clock pulse. Okay, next one, here this OPR field for the arithmetic logic unit specifies what operation we have to perform. There are 14 operations that can be performed through arithmetic logic unit. Among that 14 operation, which operation we have to perform, that can be determined by using OPR field. OPR field determines what operation we have to perform through arithmetic and logic unit. Okay. Next one is here the selection inputs of multiplexer A selects the source register, selects only the source register for the A inputs of the arithmetic logic unit. Selection inputs of B register is used for selecting a register that can be sent it to the B inputs of the multiplexer. Next one, OPR field determines what operation we have to perform among the 14 micro operations. Selection inputs of D determines the destination register. That means after performing the operation through the ALU, whatever the result we are getting, that result is loaded into the destination register. That destination register is selected by the cell D. Okay, so this is the simple description of the how a register set is connected with ALU. Next one, so this is the control word. So control word consists of 14 bits. So sorry, this is 5 bits. 3 plus 3 plus 3 plus 5, that is 14 bits. These 14 bits are nothing but selection inputs. These 14 selection inputs values can be formed as a control word. So selection inputs of multiplexer A contains 3 bit. Selection inputs of multiplexer B contains 3 bits. Selection inputs of D contains 3 bits. OPR field contains 5 bits. So total 14 bit. These 14 bit selection inputs values can be combined into a particular value. That particular value can be formed as a control word. This is called as 14-bit control word. These 14-bit control word can be divided into 4 fields. First one is cell A, second one is cell B, third one is cell D, and fourth one is OPR field. OPR field contains 5 bits. These 5 bits specifies only one operation among the 14 micro operations that can be done by using arithmetic logic unit. Next one, cell D. 3 bits of cell D is used for selecting a destination register. 3 inputs of cell B is used for selecting only one of the processor register. That can be formed as B input of ALU. Next one, 3 bits of cell A determines for selecting a source register that can be formed as A input of the ALU. Okay, now we can go for which register is selected when cell A and cell B values are binary values. That can be discussed by using one table and explained with one example. Table 1 shows encoding of register selection field. These are the register selection field. So first column contains the binary code. Next column contains SEL A. 3 bits of SEL A is used for selecting the source register. Next column is 3 bits of cell B is used for selecting only one register. Next column represents SELD. These 3 bits of SELD is used for selecting the destination register. So SELA contains 3 bits, SELB contains 3 bits, SELD contains 3 bits. Okay. First binary code is 000. We do not select any register in cell A. We do not select any register in cell B. At that time, only the input is selected. By using SELD, we do not select any destination register. Whatever the input register that is selected, the content of that input register is connected to directly to the output only. At that time, SCLA select input register, SCLB connect selects input register, and SCLD does not select any destination register, so that it can be represented with none. Next one, binary code is 001. The equivalent decimal value is R1, so that SCLA select R1 register, SCLB select R1 register, SCLD select R1 register. Next, binary code is 010. The equivalent decimal value is 2, so that SCLA select R2 register, SCLB select R2 register, SCLD select R2 register. Next, binary code is 011. The decimal equivalent value is 3, so that SCLA select R3 register, SCLB select R3 register, SCLD select R3 register. In the same way, binary code is 111. The equivalent decimal value is 7, so that SCLA select register R7, SCLB select register R7, SCLD select register R7. Next one is table 2 shows the encoding of ALU operation. Here we are specifying only 11 micro operations. So, which operation we have to perform among that 11 micro operation, that can be decided by the OPR field. OPR field contains 5 bits. Okay. So, OPR first column represents the OPR select. OPR select, it can select the 5-bit address in binary. Next one, second column represents the operation. Third column represents the symbol used for representing the micro operation. Okay, OPR select value is 0, 0, 0, 0, 0. The operation we have to perform is transfer A. That can be denoted by TSFA. Then OPR select value is 0, 0, 0, 0, 1. We have to perform the increment operation on the content of register A. That can be denoted by INCA. Next one, OPR select value is 0, 0, 0, 1, 0. Then we have to perform the add operation between the content of register A and register B. The symbol used for this add micro operation is add, ADD. Next one, 0, 0, 1, 0, 1. So the operation we have to perform is subtraction operation between the content of register A and register B. The symbol used for this subtraction operation is SUB. Next one, OPR value is 0, 0, 1, 1, 0. We have to perform the decrement operation. We are decrementing the content of register A by 1. That can be denoted by DECA. Next one, OPR value is 0, 1, 0, 0, 0. We have to perform the logical AND operation between the content of register A and register B. The symbol used for this micro operation is AND. Next, OPR value is 0, 1, 0, 1, 0. We have to perform the logical OR operation between the content of register A and register B. The symbol used for this micro operation is OR. Next one, 0, 1, 1, 0, 0. We have to perform the XOR operation between the content of register A and register B. The symbol used for this operation is XOR. Next one, OPR value is 0, 1, 1, 0. We have to complement the content of register A. That means we have to perform the complement operation. That can be denoted by symbol COMA. Next one is OPR value is 1, 0, 0, 0, 0. we have to perform the shift right operation on the content of register A. That means we have to shift each and every bit by one position to the right. That can be denoted by SHRA. Next, OPR value is 11000. We have to perform the shift left operation on the content of register A. That means we have to shift each and every bit of register A by one position to the left. That can be denoted by SHLA. So, this OPR field determines what operation we have to perform among that 11 micro operation that can be decided by using the 5-bit OPR value in binary. Next one, suppose we want to perform a micro operation R1 arrow mark R2 minus R3. Okay, how to perform this one? Here the source register is R2 and another register is R3 and a destination register is R1. Okay, so to select the source register we have to use SELA value. To select another register we have to use SELB value. We have to select the destination register, we have to use SELD value. We have to perform what operation we have to perform, that can be decided by OPR field. So what fields we are requiring? These fields we are requiring. So SELA, SELB, SELD, OPR. So this is a 14-bit control word. These 14-bit control word can be divided into 4 fields. These 4 fields we have to use. Next one, which register we have to select? Okay, so SELA is always selects the source register. So that is R2 register we have to select. What is the R2 value in binary? R2 value in binary is 010. We have to write 010. Next, what is the next register we have to select? That can be done with SELB. In SELB we have to use R3 register. What is R3 register binary value? That is 011. So that we have to write 011. Next, what is the destination register here? R1. That can be decided with SELD. In SELD we have to use R1 register. What is the corresponding binary value? That is 001. Then what operation we have to perform? Subtraction operation. In OPR field we have to write subtraction operation. What is the binary value in 5 bits? That is 00101. This is the control word. So the control word for performing this subtraction micro operation is 010, 011, 001, 00101. Okay, these first 3 bits represents the source register, that is R2 register. Next 3 bits represents another register, that is R3, that is 011. This is R2, this is R3. Next 3 bit represents the destination register, that is R1, that is 001. Next 5 bits represents the OPR field. OPR field 00101 is nothing but subtraction operation. So subtraction operation. This is the 14-bit control word for performing the subtraction operation. Okay, so in this way we have to perform any micro operation that can be represented with 14-bit control word. So these are the several micro operations that can be performed by the CPU. The first column represents the micro operation and the second column represents the symbolic designation that can be divided into 6 fields: SELA, SELB, SELD, OPR, control word. So this is Suppose we want to perform the subtraction operation R1 arrow mark R2 minus R3. So SCLA determines R2 register, SCLB determines R3 register, SCLD determines R1 register, OPR determines subtraction operation, and control word is for R2 0 1 0, next for R3 0 1 1, and for R1 0 0 1, and subtraction operation value is 0 0 1 0 1. So in this way we have to determine the example of micro operations by the CPU. Suppose we want to perform this one, output arrow mark R2. Okay, so SCLA determines R2, SCLB does not determines anything, and SCLD does not determines anything because output cannot be determined, so that we have to write none. So the OPR contains TSFA. So first SCLA value is R2, R2 value is 0 1 0. Next one is we do not determine SCLB, so SCLB value is 0 0 0, and SCLD value is also none, that can be denoted with 0 0 0, and TSFA value is all 5 zeros. So in this way we have to represent any micro operation by using table 1 and table 2. Okay. If you have any doubts for representing this micro operation, please put your doubts in the comment section. I will try to clarify your doubts. I hope all of you understanding this video. If you really understanding this video, please share this video to your friends and classmates and click on the bell icon to get the future updates in my YouTube channel after subscribing my YouTube channel. So, Divvela Srinivasa. Thank you one and all for watching this video.